Today, Professor Andrei Starinets will give a special public talk on string theory, black holes, and Quark-Gluon plasma. Let us please welcome.
Thank you. Thank you very much. So first of all, I would like to thank the Institute for very warm hospitality during the school. It seems to be a rather interesting experience. I hope also for participants, but certainly for myself. I will tell you a story about string theory, black holes, and Quark-Gluon plasma. And the outline of the story is presented here on the first slide. We will start with string theory and black holes within the context of a string theory. First of all, it's important to understand that string theory is a theory which pretends or tries to be the theory of all interactions, including gravity on the quantum level, is supposed to explain black holes' entropy. And we will talk about various formulas which arise in this context. Then we discuss the notion of perturbative and non-perturbative physics, perturbative and non-perturbative results, using a very simple, maybe oversimplified example, but I would like to stress that the duality arises in the context of such simple examples in many, many branches of physics, not necessarily in string theory. So we will continue with a simple example and consider duality as a change of variables in a functional integral, in the Feynman integral, and then finally come to what is known as ADS-CFT correspondence, holographic duality, gauge string duality, or gauge gravity duality, and there are these four terms which are sometimes used as synonyms, although strictly speaking they are not synonyms. Then we will come to physics of heavy ion collisions and talk a little bit about Quark-Gluon plasma, and then finally the punchline will be the discussion of how string theory can help to understand behavior of hot and dense nuclear matter and other strongly interacting systems. So this is the outline of this discussion. And we will start with gravity. So of course, most of you know very well that in Einstein's general relativity, there is a relationship between curvature, between properties of space and time, which are typically described by the metric tensor, and matter, which is presented with space-time, matter or energy, which in some sense is the same. So typically, you will see a picture of this type where you have a massive body, such as Earth, which is a source of curvature of space-time. And this picture is, of course, very qualitative, but quantitative story behind this picture is very well known since Einstein, and it is encoded in this set of Einstein's equations, whose exact meaning, for those of you who are not familiar with general relativity, of which I don't think there are many, it doesn't really matter. It's important to know that these equations actually tell us that the curvature of space-time, which is encoded in this metric tensor G mu, is proportional to the energy momentum tensor, which encodes energy and mass of the matter, such as, for example, this heavy object in the middle. Now, because many people are very well familiar with general relativity, let me just mention that these equations are written, of course, in arbitrary space-time. So indices mu and nu can go from 0, 1 to 3, but they can go in d dimensions over the number of dimensions which you want to consider. And nothing prevents us from considering general relativity in d-dimensional space-time. And this is exactly what we are going to do in the context of ADS-CFT correspondence. For us, the space-time will be 10-dimensional space-time where string theory lives, and therefore indices will go from 0 to 9. So there is also a cosmological constant present, lambda, which will play also an important role. But so far, let's just remember that in the context of normal 3 + 1 dimensional space-time, which we all observe around us, there are solutions of these Einstein's equations, And some of them are exact solutions. So these are very complicated equations. These are nonlinear partial differential equations, which are very difficult to solve. But sometimes, if you assume a number of symmetries, such as symmetries of, for example, spherical symmetry, like Schwarzschild did in his solution, then you can obtain an exact solution of Einstein's equations. And this is historically the first exact solution obtained almost immediately after equations were published, and they describe the metric of space-time outside of the body of mass m. So the Schwarzschild metric contains a number of ingredients, and again, for people who are familiar with general relativity, they tell a lot, and for people who are not familiar, they can just ignore the formula and just follow the qualitative words. So what is important about this formula? Well, first of all, you discover that, well, there is something strange happening if r, the distance from the center of this metric, is equal to the so-called Schwarzschild radius, which is equal to 2gm over c squared. You will see that something pathological happens with this metric. Namely, you have a singularity, so this term blows up, and this term goes to 0. Right, so this is the location of so-called event horizon. But for most objects, the pathology of this metric at the event horizon is completely irrelevant, because it happens. So if you consider, for example, normal bodies such as the Earth or the Sun, you discover that for the Earth, the Schwarzschild radius is about 1 centimeter, and for Sun is about 3 kilometers. But I remind you that this metric is valid description of space-time outside of this body. Right, so if you think about the Earth, then this metric roughly describes the space-time outside the surface of the Earth. And if we have some pathology inside, it's irrelevant because the metric, this solution, doesn't apply inside. Inside, you have non-zero energy momentum tensor of the Einstein's equations. Metric will look very different. All right. So for most situations, these unpleasant features of the Schwarzschild solution can be completely ignored. But it may happen that in some processes, all the matter is squeezed inside the Schwarzschild radius, as this happens in the process of gravitational collapse, for example, and then the location of the event horizon and the Schwarzschild radius becomes a relevant concept. So if a matter is squeezed inside the Schwarzschild radius, then we get something which is known as a black hole. So the black hole has two singularities. One of them is the singularity which we just talked about, at the location of the event horizon, and the second singularity at the center at r equal to 0. We should remember also that g mu, the metric which describes the space-time, is not a scalar, it's a tensor. And for people who are familiar with tensors and mathematics in general of tensors, of course, we all know that tensors itself are not invariant objects. If you change coordinate system, if you change coordinates to a different set of coordinates, then your metric tensor will look very different. The simple example is set of polar coordinates. You can write down dr squared plus r squared d phi squared in polar coordinates, and r equal to 0 is a singularity of this metric. Right, it's a singular point, but if you change coordinates to Cartesian coordinates, the same metric will look like dx squared plus dy squared, and there is no singularity whatsoever. So one simple question is, can you get rid of this singularity, of this Schwarzschild singularity here, by changing coordinates and therefore changing your metric to a more convenient form? And the answer is yes. There are metrics such as Kruskal-Zekers coordinates, for example, or Eddington-Finkelstein coordinates, where this metric doesn't have an obvious singularity at r equal to rs. This is not the case for the true singularity at the center at r equal to 0, and you can show this by computing the so-called invariance in Riemannian geometry, that you cannot change coordinates in such a way that get rid of the singularity in the center. And so this is a real problem from a point of view of physics, because there your solution simply ceases to exist as a meaningful concept. So what can be done about this? Well, not much, actually, to the degree that we know of, because this singularity at the center is something which is present in Einstein's general relativity, but if you try to generalize gravity, and you can generalize it in a number of ways. Well, first of all, you can generalize it at the quantum level, which nobody really knows how to do properly, because the theory of quantum gravity at the moment doesn't exist as a complete theory with well-tested predictions. So we're, seriously speaking, we don't know how to do this. You can also try to think about gravity in terms of effective theory. And this is a rather productive sort of way of thinking. It's very similar to what I described in my first lectures at this school, when we think about Navier-Stokes equations in water, right? So if you think of water at a microscopic level, you know it consists of particles, of molecules, H2O, right? There are also atoms there and quarks and so on. And there is a complicated microscopic structure. But if you go to larger and larger distances, much larger than this interatomic distance in this microscopic description, then you know very well that water and any other liquid is well described by a set of, for example, Navier-Stokes equations. And the only memory of this microscopic structure will be encoded in the coefficients, which are known as transport coefficients, such as viscosity, which remember what kind of microscopic structure was inside. Was it Quark-Gluon plasma, was it water, or any other liquid? So a similar philosophy can be applied to gravity. We don't know the microscopic structure of space-time, or whatever replaces space-time at ultra-short distances, or maybe even the notion of distance ceases to exist. We have no idea what is the ultraviolet completion of general relativity. But we know very well that at infrared, at sufficiently large distances, it's well described by a covariant theory, which is Einstein general relativity. And so, in the spirit of this Navier-Stokes analogy, you can think of adding to the action, which is Einstein-Hilbert action involving R and cosmological constant lambda, you can add all possible operators, the covariant expressions, which are compatible with the symmetries of the theory, right, and of which there are infinitely many. So in principle, you can continue adding things like, for example, Riemann terms are squared, Riemann tensor to a fourth, and so on, and various derivatives, covariant derivatives of this in the spirit of the effective theory. Pretty much like you build hydrodynamics out of this in the spirit of effective theory approach. This is actually essentially the same scheme. And you can say, well, this is great, let's just do it, right, and let's generalize our relativity and try to see what happens to the singularity. Maybe by doing this, you can resolve the singularity. So that's question number one. And question number two, if you actually add these components, these other high derivative components, then of course equations of motion will change. And if equations of motion will change, then you can go and test these equations of motion and find out what kind of coefficients C1 and C2 are there, at least experimentally. If you cannot predict them theoretically, at least experimentally you can measure them. This is of course correct, except that we know by dimensional analysis that these coefficients C1 and C2 will be proportional to the powers, in general to the powers of the Planck constant, simply by making the whole expression for the action dimensionless. You have to have these coefficients to have Planck constant to some power. And Planck length, as we all know, is a very small number in comparison to our normal scale. For example, in comparison to the solar system, right, it's 10 to minus 33 centimeters. And therefore, you can imagine that measuring all sorts of effects which are proportional to L Planck squared and higher will be rather difficult, right? It's very difficult to measure effect 10 to minus 64, for example. Right, so in principle, it's not a bad approach, but in practice it's very difficult. It's very difficult to expect that tomorrow you can measure actually corrections to general relativity coming from these terms. All we know that they must be there on general principles as far as we understand them. They must be there. And in particular, cosmological constant must be there. As Subir explained today in the lecture, it's not up to Einstein or any other person to say, well, I want to introduce cosmological constant or I want to rule it out. It's not a will of a person. It must be there because it's compatible with all the symmetries as we know them now. Maybe somebody says tomorrow, somebody discovers that there is additional symmetry in the generalized theory, which, for example, prohibits cosmological constant, and then we happily say, no, lambda must be zero because there is some symmetry which doesn't allow terms of this type in the action. But so far, despite all the efforts, we don't know of such a symmetry. I mean, supersymmetry could be a possibility, but that is not the case for this particular situation. And so it must stay there, and it's much more difficult to actually to show that lambda is equal to some small number than to show that it must be equal to 0, because then you have to explain what dynamical mechanism drives it to a particular value. So all these terms are there. And the moral of the story is that at the moment we actually don't know the good way to resolve the singularities such as the one appearing in the Schwarzschild solution. This is not actually what I wanted to discuss today. I wanted to discuss a different property of black holes, which is known as the entropy and black hole thermodynamics. So in 1972, Bekenstein suggested that the black hole should have a well-defined entropy proportional to the horizon area. He had his reasons. I won't go into those reasons. They're very qualitative. But many people laughed at him because black holes are black. At the time, it was not known that they have any temperature. They cannot have temperature associated with them. Therefore, what the entropy and this was all looked quite ridiculous. But in 1974, Hawking demonstrated that black holes do emit radiation at quantum level, and so in fact, the temperature can be associated with a black hole, and this restores the normalcy of the first law of thermodynamics. In particular, for the Schwarzschild black hole, whose metric I wrote in the very first slides, the Hawking temperature is inversely proportional to the mass of the black hole. And in particular, the black hole of one solar mass has a Hawking radiation of about 50 nanokelvin. So you can imagine, of course, it's another example that all these effects will be extremely difficult, if not impossible, to measure with all the tools we have at the moment. But nonetheless, theoretically, it was a great breakthrough, and the discovery of Hawking fixed the coefficient of proportionality in Bekenstein's conjecture. So we know now that to solutions of general relativity known as black holes, we can associate with them temperature and entropy, and the entropy will be proportional to the area of the horizon. So there are some immediate consequences of this situation. One of them is that black holes evaporate with time. So you can see here that the temperature is inversely proportional to mass. So then the mass decreases, the temperature becomes larger and larger, right? So for very small black holes, it will be actually a very hot object and so on. So you could think a little bit, and from this you deduce that the actual black hole will have a negative specific heat, which is fairly unusual but not impossible in thermodynamic systems. There is a different problem associated with the situation, which is known as information loss paradox. But Samir, in his lectures, covered this in full detail, so I won't say anything about information loss. The third item, the third consequence of the discovery of Bekenstein and Hawking was the following, and this is what led to ADS-CFT correspondence. We can ask a question: what are the microscopic degrees of freedom underlying the black hole thermodynamics? So from usual thermodynamics, you know very well that suppose we have a thermodynamic of gas, right? So we have first law, second law, third law. We can write down Carnot cycle and all these wonderful things. But we know that underlying all those laws, there is a set of statistical mechanics equations from which you can derive the thermodynamic laws of a particular system, such as a gas, a liquid, or any other system. So if you have a body such as an object, such as a black hole, which possesses temperature, entropy, and which obey the equations, these quantities obey the equations similar to, well, identical to the equations of thermodynamics, it means that there should be some degrees of freedom underlying this thermodynamics. And these degrees of freedom should be microscopic degrees of freedom, and therefore one has to find them and show that from them, by using the standard calculations in statistical physics, it follows that you have this, the laws of black hole thermodynamics, including the expression for the black hole entropy. So this was a problem, and let me remind you So how this works in practice. So the entropy and microstates, in statistical mechanics, entropy is related to the number of microstates, as Boltzmann taught us. So consider a simplest system. You have one particle with spin. Right, a spin can have eigenvalues up and down, so you have two microstates potentially. If you have two particles, then the number of combinations, you have one of them, for example, spin down, a second spin down, then spin down and spin up, and so on. There are altogether 4 microstates available for this system, and it's not difficult to show that if you have n particles with spin, the number of microstates will be 2 to the power n. So the entropy of the system will be proportional to logarithm of the number of microstates, and therefore will be proportional to n. So the question is, can we count the microstates of a black hole and recover the Bekenstein-Hawking result that the entropy is proportional to the area of the horizon? And I draw your attention to the fact that it is quite unusual, because the normal extensive systems, such as gas in this room, they of course have entropy which is proportional to volume, not to the surface area of the room. So string theory, which claims to be a theory of all interactions including gravity at quantum level, of course is supposed to provide a way to count the microstates of the black hole, and therefore a rather strong effort in the 1990s in particular was dedicated to deriving the Bekenstein-Hawking expression for the entropy of black hole from string theory. Now, Strominger and Waffa, and again, this was discussed extensively by Samir at his lectures in this school, were able to count microstates of a very special black hole in 5 dimensions. So this result coincided exactly with the Bekenstein-Hawking thermodynamic entropy, and in some sense it remains one of the greatest theoretical achievement of string theory, that you actually can do this calculation and show that what is supposed to emerge from theoretical calculations actually emerges. Now, this result of Strominger and Waffa has been generalized in many ways since 1996. And to many types of black holes, to many dimensions, and so on and so forth. And this is great work and very important and very deep work. But let me just say that up to now, we still don't know how to count microstates of normal black holes, including the astrophysical black holes or Schwarzschild black holes in 4 dimensions. There are reasons for that. And I will explain perhaps these reasons in a moment. But these reasons have to do something with the fact that when you try to count the microstates, you have to face the problem of a strong coupling. And within the context of the work of Strominger and Waffa, this was somehow circumvented by the fact that the black hole was a very, very special construction which involved a lot of symmetry. And if you have a lot of symmetry, then the number of microstates at weak coupling can be protected, the number of degrees of freedom can be protected by the symmetry, in this case supersymmetry, and it doesn't change from weak coupling to strong coupling. So what they actually did, they counted the number of microstates at weak coupling, pretty much like you count the number of states in harmonic oscillator, and then using the fact that the solution was supersymmetric, they said, and that was a theorem, that this number is exactly the same at strong coupling. And strong coupling, you have a black hole, the same system becomes a black hole, and the entropy of this black hole exactly matched the calculation at weak coupling, because it was a very special supersymmetric solution. Unfortunately, for normal Schwarzschild black hole in 4 dimensions, we don't have this option. We don't have this supersymmetry or any other symmetry which would protect the number of degrees of freedom up to some weak coupling point where you can count them as you count the states in harmonic oscillator. So this is a rather technical difficulty, but nonetheless, the fact is that we still don't know how to reproduce Bekenstein-Hawking result for normal astrophysical black holes. So nonetheless, it was some sort of a progress, and I would like to draw your attention to the fact that this shows that in gravitational systems, right, the entropy is proportional to the area rather than to a volume, as it is the case in the systems like a gas in this room. So there is something interesting, therefore, for systems which involve gravity. And this usually goes by the name of a holographic principle. So there is a hint that if you have something in d dimensions, or for example, you have a solution, gravitational solution such as black hole, then the entropy of this object does not have to be proportional to the full volume in d dimensions. It is proportional to the number of degrees of freedom on the surface of this object, and the surface of this object has one dimension less. So in other words, gravitational degrees of freedom somehow can be encoded in a theory in some other effective degrees of freedom in such a way that this effective description lives in one dimension less. So this is known as holographic principle, and it was discussed at length by 't Hooft and Susskind in the 1990s. But not before ADS-CFT correspondence was formulated, this principle was made a very concrete working proposal which can be used for quantitative calculations. So my message here is the following, that ADS-CFT correspondence or holography or gauge string duality was a direct consequence of the work on black hole entropy. And in some sense, ADS-CFT was discovered by accident in a certain sense. I mean, people didn't want to discuss this particular duality just because they wanted a particular dual to strongly coupled gauge theories, but because the work on explanation of the black hole entropy has driven them into this direction. So what about this? So what is this correspondence? So this this duality was formulated by Maldacena in 1997, although there were 2 or 3 years, at least 2 years of very intense work by, not only by Maldacena, but by many other people. In some sense, if you look a posteriori, then of course many people understood that there should be a duality of this type, but none of them said this explicitly. So in some sense, Maldacena had this courage to make this decisive step of actually putting this in a paper and declaring that there is an exact duality. So the duality is the following thing. In string theory, in addition to strings, which are which can be closed or open strings. So these are one-dimensional objects. They vibrate as a quantum object. They produce a spectrum of excitations, and they're supposed to explain, let's say, what we see at larger distances as particles and fields. Now, in addition to open and closed strings, string theory has some solitonic-like objects, or topological defects, if you want. And these topological defects are known as branes. So these are hypersurfaces which live in 10 dimensions, and they're also quantum objects. You can imagine some sheet of energy, the infinite sheet of energy, which vibrates as a quantum object, and excitations of this object can be described by excitations of open strings, which are attached to this topological defect, to the brane. So these topological defects were discovered in mid-1990s, mostly by Polchinski and some other people who contributed to this discovery. These solitonic-like objects, the branes, can be described in 2 languages. They can be described in the language of open string theory, just like excitations of various particles which are attached to the branes. So we can consider, for example, 3+1 dimensional, so-called free brane. The free brane, free stands for number of spatial dimensions. So the world volume of the free brane is a 3+1 dimensional world volume. So you can associate, if you want, this 3+1 dimensional world volume with the world we live in, with this room. And the open strings, which stretch all the way to 10 dimensions, are attached to this volume, and the end points of these strings are free to move around in this volume. So you can imagine the end point of such a 10-dimensional string as, for example, the end point. So it's a point, so you can think of this as an electron, right? And this electron is free to move in 3+1 dimensions, but not in higher dimension. So it's attached to the brane in this sense, right? And it's moving around. So for us, it's just an elementary particle, a quark or electron and so on. But it's actually the end point of this 10-dimensional string. And there are infinitely many of them. So every single point on the surface, on the world volume of this brane, is the end point of some string. Now, the strings have a spectrum of excitations, as I mentioned, and the low energy spectrum of these excitations will give us massless fields. Most of them we know from our ordinary experience, right? So these are gauge fields, such as gauge bosons, or these are fermions, maybe quarks, and maybe scalar fields, massless scalar fields. So it turns out that for a particular solution, which is known as de-free brane, these low energies, or these are low energy states. Of course, string has also massive states, which are extremely heavy, and which cannot be resolved with energies of our accelerators. And, but low energy states, of course, if we consider the situation at low energies, then of course, all of this can be organized in particular Lagrangian, and we can describe this theory. So I'm talking about a theoretical construction. I'm not talking about our world, right? So this is just an analogy that we can see the endpoint of a string as an electron, right? But in theoretical construction, this is exactly what happens. So you can describe this topological defect, which is a collection of de-free branes, NC de-free branes, from a point of view of open string theory, and low energy description of this object will involve a particular gauge theory. This gauge theory will not be QCD. It would be fantastic if it were QCD. It's not QCD. It's some theory. It's supersymmetric. It's superconformal. There are some properties of it. But it is a decent gauge theory for which I can write down the Lagrangian and energy momentum tensor, right? So this is one description of this topological defect from the open string theory point of view. I can also describe the same object, the same topological defect, from a point of view of closed string theory picture. And in the closed string theory picture, the same object with n de-free branes coinciding form a solution which can be found exactly in 10-dimensional general relativity, and this solution will be similar to the Schwarzschild solution. It will describe as a sort of a black hole or black brane. It will be a gravitational solution which has a metric, which has all the properties of the gravitational solution, similar to the solution of Schwarzschild in 4 dimensions. And therefore, but it's the same object, right? It is described in 2 different languages, but the object is the same. So it's rather tempting to conjecture that there is an exact equivalence between these 2 languages. So you have language number 1, language number 2, and then if you build a dictionary between 2 languages, then you can convert this description into this description, but this is a description of the same, one and the same object. So this is qualitatively what was conjectured in '97 and then put on a very concrete basis in the beginning of 1998 in these 2 papers by Gupta, Klebanov, Polyakov, and by Witten. So let me give you a very simplified description of duality, which is actually due to a well-known philosopher, Ludwig Wittgenstein, and who, of course, knew nothing about string theory. I must confess that this slide was stolen from the talk of Shamet Kashru in New York in February of this year, but I liked it so much that I want to reproduce it with credit to Shamet, or Wittgenstein for that matter. So there is an object which Wittgenstein actually borrowed from an old German newspaper published at the end of 19th century. And this object, depending on how you look at it, right? So if you look at it sort of horizontally, you can see a duck. And if you tilt your head and look at from that perspective, you can see a rabbit. But it's one and the same object, right? So which description is right? Well, both descriptions are right? And both descriptions are adequate. So you can describe it in the language of a duck, and you can describe the same object in the language of a rabbit. But it means that there should be a dictionary between the rabbit description and the duck description, and this dictionary better be one-to-one, so it should describe the same one and the same object. So this is an example of duality, and this is exactly what happens in ADS-CFT correspondence. So let me give you another example, and especially for people who deal with functional integrals. So this perhaps will be familiar. So when I say that one picture is equivalent to the second picture, and we need to build a dictionary between the 2, this is all philosophy, but we want something quantitative. We want equations. We want to understand how to convert left-hand side to the right-hand side and vice versa. How can we do this? Now, we deal with quantum field theory typically using Feynman path integrals, right? So something like we want to compute a partition function similar to this, just like this object here, written schematically. So we have the action, and we integrate over all fields which enter this action. And maybe there are some parameters which enter our Lagrangian, such as masses, for example, or some other parameters in the game. So note one thing. So this integration variable phi, the field, is actually a dummy variable. We integrate over it. The partition function doesn't depend on phi. Just like in the ordinary integral, you integrate over dx, but you can change variables from x to y. It doesn't matter, right? So the integral remains the same. So here is the same. So partition function remains the same, and z will depend only on the parameters alpha. So if we know how to calculate this path integral, we know the theory completely. Right? We know correlation functions and so on and so forth. So this is a highly non-trivial task, and normally one resorts to approximations. So for example, one can expand this expression for small alpha and use perturbation theory and write down Feynman diagrams and then analyze them, and this is normally what is done. So here is another oversimplified example, which I promised you in the beginning. So this oversimplified example is a simple integral from 0 to 1 of this wonderful expression. Well, x here is a dummy variable, right? And the result z of alpha depends only on alpha. But suppose, and we know how to write down the exact answer. Of course, all of you know. But suppose we don't know how to integrate this expression. We only know how to compute very simple integrals, such as integral over dx is equal to x plus a constant. What could you do? Well, you can try to do something with this expression. For example, you can expand it for small alpha. So suppose your alpha is small, then you expand it. The very first term will be exactly of the form integral from 0 to 1 of dx. And we know how to compute this. This is equal to 1. So the prediction of perturbation theory here is that your partition function z of alpha is just independent of alpha to very small alpha. Is it a good prediction? Well, it's not so bad. So here is the exact answer, z as a function of alpha for all alpha, right? And for very small alpha, z equal to 1 is not such a terrible approximation. Of course, we want to do better. And in order to do better, what we can do? But we only know how to calculate integral of dx. There is nothing else. We don't know anything else. What can we do? We can try some trick. We can try to change variables in this integral in order to reduce it to the integral we know how to calculate. Let's try to do it. Well, we know a wonderful identity from trigonometry that 1 minus sine squared y is equal to cosine squared y. Right? And this is enough to make change of variables, and then change in variables, you arrive with very simple manipulations, you arrive to the integral from 0 to something of dy. And we know how to calculate this integral from perturbation theory. So you reduce the problem to the original method of calculation via change of variable. And immediately you get the exact result. Right? So this is roughly what happens when you consider ADS-CFT correspondence or the duality, the gauge string duality. You have a partition function in quantum field theory of a particular type, which arises from string theory in 10 dimensions of very specific type, with a well-defined Lagrangian. And this theory has a partition function, which in principle you can calculate perturbatively. But suppose you want to know a non-perturbative answer for alpha which is not small. How can you do this? This duality tells you that there is a dictionary which maps the degrees of freedom, the picture, open string picture, into the closed string picture. And it turns out that this map is such that in the process of mapping, you convert the parameter alpha, which is a coupling constant in this theory, in the open string picture description in quantum field theory, into 1 over alpha. So this duality is so-called strong weak duality. If your alpha is very large, you can use the right-hand side, and here is a partition function of this gravitational configuration, but now consider it at weak coupling, at 1 over alpha. So if alpha is very large, so this side, right-hand side, is perturbative, and you know how to calculate perturbatively, and everybody knows how to calculate on the right-hand side. So since you have a dictionary between the two sides, if you are interested in non-perturbative physics on the left-hand side, you can use the right-hand side to derive any answer about a theory you want to consider. In particular, you can derive answers for this theory considered at finite temperature and density, in equilibrium, out of equilibrium, in any quantum states you like. And this is very important because there are not so many methods which allow you to consider especially non-perturbative, especially non-equilibrium configurations of quantum field theories in general, or even quantum mechanical systems in general. All right, so, well, I guess, yeah, so this is the only thing I want to add to this picture again is that it's a tool. So we have a certain mathematical construction which is coming from a string theory, but it's a mathematical construction which is completely independent of the status of string theory as the theory of nature. We don't care. Maybe some people would love string theory to be the actual theory of particles and fields and underlying theory of particles and fields. Here, we don't care. This is just a construction which follows from 10-dimensional configurations of string theory, which are mathematically completely viable constructions, and we don't really care whether this describes nature, but it allows us to describe via this duality very specific type of gauge theories and describe them completely non-perturbatively. So this is the key. This is a key point. So now let me talk about the possible application. So I said that, fine, so we can compute, we can take our quantum field theory with Lagrangian, Hamiltonian, and so on, and compute whatever we want. We want to compute, for example, correlation functions or spectral density, so how quasi-particles behave at strong coupling, anything we want to compute. The question is, okay, fine, so this is a theoretical playground. Could it be useful, at least qualitatively, for some real physics? So one possibility, or one avenue of application of these calculations is the heavy ion collisions, which I described in my lectures yesterday. And these collisions, so they collide the ions of gold and or lead. And here is a picture that shows you, so the beam of the collision, so the line of the collision is going into the screen, and you have hundreds and even thousands of particles, about 10,000 particles, hadrons, which are flying out of the center of this collision. And this is all very complicated, but fortunately we have wonderful people, experimentalists, who actually built huge detectors, wonderful detectors that allow us to track these residual particles and measure all their properties, collision by collision. How they do this, don't ask me, but they do it, and this is fantastic. So as a theorist, of course, we draw all these cartoons, right? And the cartoon is the following. So we have this collision of these Lorentz contracted pancakes, the heavy ions, and they create some initial state. And then this initial state expands. The expansion is described by relativistic hydrodynamics, Navier-Stokes equations, relativistic Navier-Stokes equations. And then the state hadronizes, and then eventually it is converted into hadronic gas, and this hadronic gas is detected by these giant detectors. So the time scale of the process is very tiny, 10 to the minus 24 seconds. But if you forget about this smallness and just think about this as about T star, some particular scale, then there is actually a rather dramatic evolution from through all these processes, which involve processes of around 1.2 T star up to 10 T star. So we have a pretty big window in terms of a time scale, in terms of this time scale T star, which allows us to describe all this evolution from the initial state up to the final state. Now, how can we do this? How can we describe this? Well, in order to solve this, to provide this description, evolution of this fireball of this plasma, we use relativistic Navier-Stokes equations. In order to write down these equations, we need some input. We need equation of state. We need to understand thermodynamics of this nuclear matter, meaning thermodynamics of QCD, but we also need transport coefficients. We also need transport, which means kinetics, first and second order transport coefficients, but we need all of this in the regime of intermediate coupling strength. Then alpha QCD, alpha strong at the energy level of Rick is of order 1. It's not very small parameter, and therefore we cannot really expand things in perturbation theory. So this is an intrinsically non-perturbative problem. I would like to stress that we also need to know something else. In addition to thermodynamics and kinetics, we also need to know various other parameters, such as initial conditions, thermalization time, freeze-out conditions, and so on. So it's not one-to-one correspondence. If I give you a value, for example, of shear viscosity for QCD, it doesn't mean that it's the only parameter that has to be matched with experimental data. So it's something to keep in mind. So here's another plot which I was drawing yesterday. This is a plot of energy density normalized by energy density of the ideal gas. It shows you this crossover transition at a temperature of about 170 MeV, and this is a cartoon of the lattice data supplemented with some perturbative calculations. So at super high temperatures, our nuclear matter behaves as ideal gas of quarks and gluons. But if you ask how far in this plot you have to go in order to describe these curves by the expression relevant for ideal gas of quarks and gluons, the answer is T over Tc must be of the order of 1,000 at least. And therefore, in this plot, you have to go all the way to the right in order to describe this in terms of ideal gas and corrections to the ideal gas. Whereas actual experiments are done around here, and you may say, well, it's not so bad. Look at this plot, right? The difference is roughly 25%. So yes, I can use the perturbative description here, maybe with some corrections, maybe with 5-6 loops, and perhaps I will provide an adequate description of pressure, entropy, and equation of state. And this is indeed the case. It's not so bad as this plot shows, but it fails miserably when you try to do the same for transport coefficients, such as viscosity. Because for things which are described by thermodynamics, the difference is of about 20%. It's true. But for transport coefficients, such as viscosity, the difference is orders of magnitude. And then they're very sensitive to coupling. And therefore, it's very difficult to rely on calculation somewhere here in order to describe somewhere here, because the difference is so huge. So let me describe in a few words the situation with quantum field theories at finite temperature and density. So you can divide all properties into equilibrium and non-equilibrium or near equilibrium ones. And in equilibrium properties, you have entropy equation of state. And you can either use perturbative QCD in order to calculate this, or you can use lattice QCD in order to calculate non-perturbative properties. So these are static properties which don't involve explicit reference to time. Now, when you are out of equilibrium, then you compute transport coefficient, emission rates for various particles, and so on. And here, you can also rely on a fantastic apparatus of kinetic theory, which was developed after Maxwell and Boltzmann and other clever people. But it has some limitations because it is a perturbative apparatus. And if you come to non-perturbative domain, then there are no ways, there are no tools which allow you to compute whatever you want to compute. And this is why holography and why ADS-50 correspondence, although it deals with systems which are not related to these experiments of heavy ions, so these are not QCD systems, which are these are gauge theories of different type, but nonetheless, results which you can obtain in this class of theories are of interest simply because there are no tools available to penetrate this non-perturbative region in any way. So one of the quantity that is of interest to this heavy ion collisions is the shear viscosity. So let me remind you what the shear viscosity is. It's a measure of internal friction in a liquid or gas. So suppose you have two layers of liquid or gas moving with slightly different velocities. So you have molecules of one layer penetrating the other layer, right? So they move in all directions. In particular, they move up and down, and therefore they transfer momentum. They transfer the horizontal momentum from, for example, from faster layer to lower layer, and vice versa. And therefore, at some point, due to this transfer of momentum, the two layers will equilibrate. Eventually, we'll have the same velocity. So this is a measure, and viscosity in this perturbative, in this dilute gas, if you want picture, viscosity will be proportional to mean free path. How far one layer penetrates particles, or one layer penetrates the other layer, and vice versa. So this is what was discovered by Maxwell at the end of 19th century. And this applies very well to gases. So this calculation in which viscosity is proportional to mean free path, you can, of course, use sophisticated theories like Chapman and Skog and so on for Boltzmann equation, kinetic equation, Vlasov equation, so on and so forth. But the ultimate truth is that everything will be proportional in some sense to mean free path or mean free time, right? So this is the eigenvalue of your kinetic operator. And it only works if you have sufficiently dilute system. So what happens for liquids? So for example, viscosity of water is a rather difficult thing to calculate. There are some phenomenological theories. One of them is due to Frenkel. I will not really describe this in any detail. I can only say that these are calculations done on phenomenological grounds. So you assume something about the liquid, you draw some picture of the liquid, and this is completely sort of out of your head, and then you start. It's not so silly, right? And phenomenology is a great thing if you don't have access to microscopic degrees of freedom description from first principles. Of course, what you can do. And Frenkel built a rather successful theory around 1926. Of viscosity of liquids, but the disadvantage of this theory was that it was a theory ad hoc, right? So it was a theory sort of based on these phenological assumptions, and it's not coming from any microscopic details. And what we want is some fundamental description of the same property. So the bottom line is that, of course, we can measure viscosity of water in basically school experiments. I mean, I did it in school, for example, at some point, or university experiment. But we have absolutely no idea how to compute viscosity of water from microscopic theory of water, meaning H2O, right? So there is no way to compute it. We don't know how. So, well, we have this duality, which allows us to compute non-perturbatively properties of a gauge theory, a particular gauge theory, using this dual picture which involves gravity. So what do we know about gravity and particular deviations of gravitational solution from equilibrium? So we know that unperturbed black holes are characterized by a collection of global charges, total mass of a black hole, total angular momentum, total electric charge, and so on. And there is nothing else. This is usually known as null-Hare theorems, very important. So, okay, so these are undisturbed black holes. What about, well, I just remind you that a thermodynamic system in equilibrium is also characterized by the collection of conserved charges, right? In microcanonical ensemble, you fix the total energy, total angular momentum, total charge, electric charge, or any other charge, you have a system. So it is, of course, this manifestation of this duality, or if you want, a similarity of black hole thermodynamics, which Bekenstein and Hawking were talking about, right? So you have a direct relation between black holes and a system in thermal equilibrium. But what happens if you perturb the system out of equilibrium? Right, you perturb the system out of equilibrium, water, for example, right, you induce some processes such as diffusion process, the sound and turbulence and so on and so forth. And what happens if you perturb the black hole from equilibrium? Well, so for example, you take a black hole and throw a brick into a black hole. What will happen, right? So black hole will not like it, it will emit gravitational waves. It will eventually settle in the final state, which also will be characterized by the total mass. And now the total mass was initial mass plus the mass of a brick. But before it happens, it will produce some excitations, right? It will produce some gravitational waves, right? So this is similar. So there are some eigenfrequencies of a black hole emitted as a process as this result. And this is similar to what you do with any other body, right? So any system will have a spectrum is characterized by the system of eigenmodes, eigenfrequencies, right? So black hole is not an exception. So why this is important? Yeah, so just one slide to show that this is not theoretical, purely theoretical construction. So you can have all the signals from LIGO and so on and so forth. And these eigenfrequencies are visible in the signal, they are known as quasi-normal modes. Quasi-normal because they have non-zero imaginary part, unlike normal modes, which are purely real. But they're visible in the signal, so these are things which can be studied in experiments with gravitational waves. So this is probably the most important slide of my talk. And we can wake up for a second, well, for a minute. So we have, so remember, we have a duality. We have a description, so we have a quantum field theory. We have a quantum field theory, suppose gauge theory with Lagrangian and so on, partition function, whatever we want, which is in thermal equilibrium. Thermal equilibrium is characterized by a collection of conserved charges, temperature, and entropy in 4 dimensions. We have, via change of variables, provided a dual description in terms of gravitational degrees of freedom to the same system. And this system, this dual description at finite temperature, will contain a black hole with certain Hawking temperature and Bekenstein-Hawking entropy, which are matched to these T and S of the system. Right, so there is a dictionary which allows us to calculate from this side to this side. Exactly, so it's not philosophy, it's a quantitative description. Now, how about deviation? So I deviate the system from thermal equilibrium. For example, I deviate my density of charge and will induce some current. Right, the current will flow, and the current will flow according to the diffusion equation right here. And diffusion equation will be characterized by the diffusion coefficient d. This is transport coefficient, for example, which we want to calculate. For example, we want to calculate the diffusion coefficient at strong coupling, where we don't know how to calculate from perturbation theory. Well, in Fourier space, this diffusion equation is characterized by the eigenfrequency, which is purely imaginary. Here it is, right? This is an imaginary. This is a frequency which has no real part, just an imaginary part. So what happens on the left-hand side? Well, I have a metric G naught. So, for example, Schwarzschild metric, and I perturb my black hole or black brane, and it will emit gravitational waves. So I have to solve, I need to find the spectrum of these waves by solving, by linearizing my Einstein equation around G mu node. I can easily do it. I can write down equations obeyed by these perturbations, for example, H mu or A mu if there are some other fields present. For example, this is Reissner-Nordstrom solution. There are other fields present which are coupled to H mu. So I can linearize my Einstein's equations, and I get equations of the type box acting on H mu or box acting on A mu equal to 0, plus boundary conditions. Now, boundary conditions are important here because we have a horizon, and classically, whatever information goes into the horizon disappears there forever. So this means that the boundary value problem for these operators is a non-Hermitian boundary value problem. It's like in quantum mechanics, suppose you have infinite wall, and one wall is leaking, so you can have wave function which goes away, right? It disappears forever. So this means that the operator, the boundary value problem, will produce spectrum which will not be purely real, like in Hermitian boundary value problem. It will be so-called quasi-normal spectrum, which allows for imaginary part. There is some dissipation in the system which is present due to the horizon. But this is precisely what we expect on the left-hand side. We expect frequencies which contain non-zero imaginary parts. So it's a quantitative dictionary, so it's known very well how to match this frequency to the frequency here, and how to extract the necessary coefficient d, in this case diffusion coefficient, just by computing the quasi-normal spectrum of the dual black hole, dual background. So this is the main methods which is used to extract transport coefficients of these plasmas. So, for example, this is the actual calculation of one of the quasi-normal modes of this black brane, and this is the lowest quasi-normal modes in the infinite spectrum. And look at the structure of this dispersion relation for this mode. It has non-zero imaginary part here, I divided by 6 pi t k squared, and it has also a non-zero real part. Now c here is the speed of light. And you can compare this expression, which comes from dual 10-dimensional, 5-dimensional gravity. You can compare this expression with what you expect from the actual quantum field theory when you excite sound waves in this system. Now the sound waves have they have very well-known dispersion relation of this type. The first term will be linear in momentum k, and there will be a coefficient Vs, the speed of sound, in front of this, and then the attenuation of the sound will be proportional to the shear viscosity, or better to say, to the ratio of the shear viscosity to the entropy density. But we have a dictionary between the right-hand side and left-hand side, and this is a quantitative dictionary. It tells us precisely that this expression, the quasi-normal frequency of a black hole, this specific quasi-normal frequency, must be identically identified with the frequency of the sound wave. And you can match the coefficient in front of the appropriate terms. So it tells you that in this particular theory, which happens to be conformal theory, speed of sound is equal to the speed of light divided by square root of 3. And we know that this must be so by conformal invariance. This is just a fact of life. And we can also compare the imaginary part term. And the imaginary part term tells us that the ratio of shear viscosity to entropy density, if I restore fundamental constants, it will be equal to h bar divided by 4 pi k Boltzmann. And of course, there are corrections to this result. So I remind you that this calculation is done at infinitely strong coupling. Right? Then you lower the coupling, you expect corrections to this, but the leading infinitely coupled result is written here. Okay, so for this particular theory, so I'm taking only one example, and for this particular theory, wherefore we can write down, we can draw a plot of the dependence of the ratio of shear viscosity to entropy density on the coupling constant lambda. Well, we just found that at infinitely strong coupling, when lambda is equal to infinity, it's equal to 1 over 4 pi, right? I put h bar and k Boltzmann to 1. Then you can compute corrections to this result by using high derivative gravity terms, and the correction happens to be equal to some number divided by lambda to the power of 3/2 with a positive sign, so a plus sign. So it goes up. We don't know what happens in between. This is difficult to calculate, but we do know what happens perturbatively. Perturbatively, ratio of 8 over s is, roughly speaking, proportional to 1 over lambda squared. Let's forget about this log for a second. 1 over lambda squared, this is basically kinetic theory. Remember, I told you that this is roughly, in Maxwell kinetic theory, this is proportional to some number times the mean free time, or mean free path, for speed of light is the same, right? So some mean free path will be proportional, as you remember from elementary kinetic theory, 1 divided by n sigma, where sigma is the cross-section of interaction. Cross-section of interaction will be at leading order will be proportional to lambda squared, right? So this is kind of expected result. Of course, the presence of this log is very important, but let me not go. It's actually, this calculation is technically is much more difficult to do than this calculation. Here it's from coupling, surprisingly so, but this is correct. So you can also think of why. So this suggests that when coupling goes to 0, viscosity becomes infinite, right? So for ideal gas, strictly speaking, viscosity is equal to infinity, which is a little bit counterintuitive. So I let you think why this is so. So these are type of results which we can extract from this duality. Is it useful for RIC? Is it useful for heavy ion collisions? In some sense, in some qualitative sense, yes, it is useful. Because what people who analyze these phenomenological data coming from RIC LHC and heavy ion collisions, they solve Navier-Stokes equations with particular value of transport coefficients embedded into these equations, right? They don't know what is 8 over s for QCD. Nobody knows at this regime of coupling, right? Nobody knows. So what they do, they simply solve these equations and vary this 8 over s as a parameter in the theory, right? What you can do. So if you vary this parameter, so what happens, this plot shows what happens. So these are some experimental data, and these curves, the green, red, yellow, and blue, are curves of a prediction of solution of relativistic Navier-Stokes equations with different value of shear viscosity over entropy density. So the tendency is obvious. If the ratio of 8 over s is very small, then this curve goes too high. If the ratio of 8 over s is too large, it goes too low. The perturbative result I won't even show here because it will be completely flat, so it's complete disaster. But But if you try to ask a question, which number for 8 over s, which value for 8 over s is kind of compatible with what you see experimentally, the answer is actually interesting because 8 over s, which is compatible with experimental data for QCD, right? So not for this theory, which string theory was dual to, is actually not very far from 1 over 4 pi. So this is you can say this is a complete coincidence. I mean, this has nothing to do with the actual calculation. But nonetheless, the tendency, and this may be true, it may be indeed a coincidence, but the tendency is obvious, and tendency is obvious from the previous plot, that transport coefficient is very sensitive to the value of coupling. And once we go to intermediate coupling or strong coupling, the value of 8 over s becomes very low, very small. Right? And this is what we see here, although we don't have, strictly speaking, the calculation for QCD itself. We see it here that this ratio, if our system is sufficiently strongly coupled, then this ratio is of the order of 1 over 4 pi, rather than 200 times larger than this value, as would be predicted by perturbative physics. So then we can speculate, and let me finish by these plots, which are speculations, but I think these are old speculations, but they're still interesting. So we found that for infinitely strongly coupled systems, in the limit of coupling equal to infinity, the value of ratio of shear viscosity entropy density is equal to 1 over 4 pi universally for all systems. You take any system for which you know that infinitely coupled point has a gravity dual description, and this ratio is guaranteed to have this value of 1 over pi. The corrections to this, of course, are different for different theories, right? So obviously, the corrections are not universal. But the fact that it is a universal number is sort of interesting, and you can try to speculate. So if you take various normal substances like xenon or CO2 or H2O, helium, and so on, and see how the same ratio behaves as a function of, for example, temperature and pressure, you discover that all of them have a certain minimum at a certain value of a temperature or pressure. And you may wonder if perhaps there is a quantum limit or the absolute minimum for these plots, and this absolute minimum is provided by the ratio of 8 over s, which is extracted from black hole physics, namely h bar over 4 pi k Boltzmann. Well, you can just go and test, right? So you can plot these things for various substances. The lowest one among normal substances is helium. So helium comes as 8.8 times this value of 1 over 4 pi. And here are some plots for water at different pressures, and helium again, and some cold Fermi gases that people also try to calculate this. In fact, they claim that for the atomic gases, you can bit the helium limit and put it at 5.5, the 1 over pi value. But we don't know what happens in QCD, right? So that's the unfortunate truth. It's clear that there must be, from these plots, which are kind of reflect what we know about it, it's clear that there must be some minimum somewhere, but whether this minimum has anything to do with this 1 over pi and how close, how high it is, it's not entirely clear. So these results from Rick, this mention of Navier-Stokes equations, suggest that Quark-Gluon plasma appears to be the substance which we can make in the laboratory, right, in experiments, with the lowest value of 8 over s, not with viscosity, as sometimes incorrectly stated, including the website of, okay, so let me not say more. Yeah, so in some places, so sometimes it's said that, oh, the Quark-Gluon plasma is the substance with the lowest viscosity. It's wrong. Please, viscosity of Quark-Gluon plasma is not very different from viscosity of glass, right? It's very large, but the entropy is also very large. So the ratio happens to be the lowest among the substances we know of, right? But not the viscosity itself. Please don't make this mistake. Okay, so let me conclude. So this is an illustration of how duality can can help to understand, at least qualitatively, certain features. So what we covered, so string theory is partially successful in explaining entropy of black holes. Black holes have entropy and temperature and behave like thermodynamic systems, and we think we know why, because of the holographic principle. So the work of string theories on black hole physics has led to the, I would say, accidental, perhaps maybe it's too strong a word, maybe, I don't know what was in the mind of Maldacen and others, but it seems to me that this was one of these essentially accidental discoveries of ADS-CFT or gauge string duality. And this duality can be viewed as a non-trivial change of variables in path integral. We know it works. It has been tested in numerous examples. So over 50 or almost 20 years, right? So every single test, so if this duality fails, at least one test is dead completely, right? So, but so far it didn't happen. So many people sort of believe that yes, it must be true. It remains a conjecture, right? So it's not rigorous proof is still lacking, but nonetheless, people think that because it survives so many tests, that most likely it is actually a true duality. Now, the duality can compute field theory quantities at strong coupling, and these computations help to explain properties of the Quark-Gluon plasma, for example, low value of shear viscosity entropy density ratio, and some other properties as well, and are of great interest for other strongly interacting systems, for example, in condensed matter, in various condensed matter systems. Now, let me add this last line here by saying that the duality is a two-way street, of course, right? So we have a dictionary from right-hand side to left-hand side, but also vice versa, right? So can it be used to understand strongly coupled gravity via weakly coupled, for example, thermal gauge theory? So it would be tempting to say that we can understand the properties of black hole, the evolution and singularities, and resolve the singularity of black holes by writing down some equations that would tell us how to relate these questions to the questions of the thermal gas of gluons, so thermal gas of gauge theory particles. Unfortunately, this direction is not explored to the degree the opposite direction was explored. If you count the number of papers that were written by applying duality to explain strongly coupled gauge theories via weakly coupled gravity, compare this to the number of papers which were sort of attempting to use the duality in the opposite side, I think the ratio would be something like, maybe 20,000 to 1 or something like that. So it's really not a very well explored part of the duality. And since this is a summer school, so let me finish by asking people who are interested in the subject maybe to try to improve the situation and perhaps explore this duality also in the opposite side. Thank you. Questions?
Measured there. So, but you said that when we throw let's say something to it, then we can still measure on it. They can be converted, but we somehow disturb it by throwing it. So how can that be changed?
Yeah, you can throw a brick into a black hole and wait for a very long time until the system settles in the final state, and this final state will be again an equilibrium black hole. Yeah. Other questions?
So if the cross section goes up, the mean free path goes down, and the viscosity decreases. That's Maxwell's theory.
Yeah.
It sort of seems counterintuitive, doesn't it?
Yes. Yeah. So.
Isn't it the ability to transmit momentum from one layer to another?
Yeah. So for weakly coupled gas, right? So it's proportional. So it's proportional to mean free path, right? So if the gas is not ideal but very weakly coupled. All right. So what will happen is that the mean free path will increase, and therefore viscosity will increase. So the closer you get to the ideal gas, the closer viscosity comes to infinity. All right. So this simply reflects the fact that if you So if you have two layers of weakly interacting gas, then they penetrate into each other so deeply that it's very difficult to create a shear.
Oh, I see. Yes.
Yeah, but of course, taking the absolute limit here is not defined, because for ideal gas, obviously, there is no interaction to begin with, right? So that won't work. But formally speaking, the viscosity of ideal gas is infinite, right? So, in this sense. Other questions? Yes, please.
What other problems can these methods solve? What are other people trying to solve in these days with this method?
What we're trying to solve, or what has been solved? It's right. So there's well, as I mentioned, the duality. So duality has an advantage and a weakness. And a weakness I already mentioned, that it applies to a certain class of quantum field theories, but not to the theories that you would like to explore. So for example, not to QCD. If you come to me with your favorite Hamiltonian and ask what happens to strong coupling, most likely I will say, well, I have no idea, because there is no dual to it. The strong side of duality is that because of this equality of partition functions, roughly speaking, right? You can compute whatever you want to compute, really. So you can, and not only static processes like pressure and entropy and so on, but also real-time processes, including, for example, non-equilibrium physics. So one of the avenues of exploration is to understand how non-equilibrium processes, for which we don't really have, we have good description of near equilibrium physics, but for highly non-equilibrium processes, it's extremely difficult to put a formula, right? So here you have a laboratory which allows you to say, to compute what actually happens, how the system comes to thermal equilibrium, how the degrees of freedom interact. So for example, you have some experiments with liquids, right? And you want to see at strong coupling, right? So what kind of degrees of freedom interact, what kind of quasi-particles do you have? So at least qualitatively, of course, you don't have a dual specifically for, let's say, for water or glycerin or some substance, right? But qualitatively, these things are the same. So you can have an experiment with neutron scattering, which tells you how the degrees of freedom will interact and what happens if you, when you have a system at weak and strong coupling. And you can predict those properties, at least qualitatively, by looking at a dual system similar to this one. Or you can study. So one of the open questions for a long time in this heavy ion collisions was the question of why hydrodynamics works so well to describe. So it works very well, far beyond the naive set of limits where it's supposed to work, right? And the conjecture was that perhaps it has something to do with strong coupling. Perhaps it works so well because the coupling is strong. Maybe the sort of domain of validity of hydrodynamic description changes with coupling. And you can use duality to actually confirm this. You can do the calculations and say that yes, it will be a rapid thermalization because it depends on the coupling and strong coupling. The system will thermalize more rapidly and things like that. So again, it's a theoretical laboratory. Unfortunately, it's not like it can, it's not a tool to give you viscosity of water, but it's a tool to understand qualitatively behavior of various substances and quantitatively behavior of limited number of quantum field theories. So there you can compute everything from scratch until the end, right? So that's, I think, quite useful. Other questions? All right.
So let us sense it.
Thank you.